this even better. Okay, go ahead, Efren.
Yeah, great. Yeah, thanks very much. Thank you for the introduction, and thanks everyone for showing up on a Monday in the middle of the summer. I've planned for maybe 30 to 35 minutes, so I hope it will be worth your while. So before I begin, I wanted to thank Joe, the group, and the lab for hosting me. The program has really been amazing since I arrived, so I'm excited to be here. So yeah, I've bothered a few people with questions here and there, and thanks for the help. So yeah, so first just about myself, let's see. Yes, I'm an associate professor at the Technical University of Denmark, working in the acoustic technology group, and I will be visiting responsive environments until mid-October. And I'm here with my family, so my wife, who's our partner, who's a researcher at RPI, and our son, who's having a really great time. So yeah. So during the time that I'm here, I'm happy to learn about the stuff that they're doing in different groups and so on. So of course, feel free, and I would appreciate this, yeah, having a chat. So I'm visiting from DTU, which is one of the main technical universities in Europe. It's located in the Copenhagen area, and it was founded about 200 years ago by Hans Christian Ørsted, who is the scientist who discovered electromagnetism. And one of the key areas in the university in Denmark is acoustics. There is quite some, as you know, Denmark is a fairly small country, but the acoustics industry is quite large compared to the size of the country. So there's a strong tradition in audio, transducers and sensors, hearing aids. About half of the hearing aids of the world are made by Danish companies. So for such a small country, it's quite a big thing. And also in DTU, also it's one of the key areas. So we have a fairly large group of researchers that are working in different aspects of acoustics. Of course, physical acoustics and room acoustics, transducers, hearing and perception, vibration, computational methods, and so on, right? So depending on how you count it, and across different departments in electrical engineering, health technology, wind energy, and so on, there's somewhere between 60 to about 100 staff working on related topics to acoustics. We also host the largest international master's program in acoustics in Europe. So currently we have an intake of about 45 students. So in total, about 90 active students in the world. So that also gives a quite dynamic environment in terms of teaching and learning at first. Yeah, and that's us there. You can see here, these are the labs, and that's the office space. We have, as you can see here, this is our large anechoic chamber, some audiovisual, like the smaller anechoic chambers, reverberation rooms, and a lot of space for experiments, which is it's quite fun. And of course, I mean, if anytime you're in Copenhagen and want to visit, have a few demos and so on, I would be more than happy to show you. And also, if you want to visit, to stay with us for a while, our doors are certainly open. So yeah, some of the facilities. So here we see the what's called the audiovisual immersion lab. So basically, sound for reproduction room. Are the large anechoic chamber that we were seeing earlier. Some of the reverberation rooms. We also have a vibroacoustics lab and physiology labs, psychoacoustics, and so on. So yeah, it's quite fun. In my group, the work that we do is mostly concerned with sensing, analyzing, and reproducing sound fields. So we're trying to advance the way in which we both measure, manipulate, and interact with sound. And I think that leads me to the topic that of the presentation today, which is how to measure acoustic fields over large spatial domains. If we go a bit back in time and think of, say, conventional acoustic sensing, the dominant notion has been you have some acoustic wave and you record pressure fluctuations as a function of time in one point or a collection of points, right? And that, of course, acoustic technology and transducers have evolved dramatically in all this time, but that notion is pretty much the dominant one when we think of sensing sound, right? However, as you know, and that's what the first carbon microphone, quite old now, but already we go before that to the phonograph and these very early instruments. It's typically being just pressure time at one point space. But as you probably know, the spatial properties of sound are extremely important to us. We do relate very much to our environment through the spatial properties of sound. Also, that determines our communication and basically how we relate acoustically, given in the space that we are here now. Right? However, it is far more challenging to capture spatial properties of sound. Main reasons, so spatial sampling, of course, if we think of the wavelength span by audible sound, like we have in the low frequency, and wavelengths that are as large as 17 meters, and the high frequency range of audible sound will have like wavelengths that are as small as 17 millimeters, right? So when you think of sampling in space domain, these small wavelengths, then it becomes practically unfeasible to recover like a full wideband audible sound field in space domain, right? So there is inherently a band limitation. Of course, then the more complex the domain is because of its boundary, the topology, bound materials in the boundary, and so on, the problem, of course, grows in complexity. And also, if we look at very large apertures, then that's just also more difficult, right? So this is the problem that I specifically am going to talk about today. How do we measure sound over these large apertures? So say, for example, a situation like this one, we have some sound field and we are interested in capturing this space. And this problem is, say, relevant for, of course, communication, immersive technology, audio, architectural design, assistive technologies, and so on, right? And here, I guess there are three main approaches or lines of approach that one could think of, being directly distributing sensors about space and say, okay, let's just scale up the sensing and just measure everything that we can. And then this is costly, and as I said, because of the challenge of having some fairly small acoustic wavelengths, it's often unfeasible to just scale up the measurement, and also becomes very, very intrusive, right? Two other approaches that these are the ones that I will talk about today, is either using novel sensing principles, which are inherently spatial. So instead of actually having a sensor at a point that measures an acoustic signal, I will talk about the acousto-optic effect and the acousto-optic interaction as a way to have a measurement method that is inherently spatial. And then another approach, which is, it's relevant both for novel sensing methods as well as traditional microphone array methods, would be sound field reconstruction approaches. So basically, how to predict the sound field at points that have not been measured. So for example, in a situation like this one, imagine that you have a compact array of microphones here in the center. So you know what the properties of the sound fields are here. And then you try to extrapolate it as far as possible to predict over the entire aperture. Or if you have a distributed set of sensors or sensor arrays, how to interpolate between them in a meaningful way. So these are the two things that I will talk about. The first one being the acousto-optic sensing. I don't know how many of you, I guess you've heard or you know what the acousto-optic effect is. It basically refers to the interaction between light and sound. So essentially, light is refracted and its speed is changed very slightly as it traverses the sound field. So For example, in a situation like this one, the black dots represent just a fluid medium, and there is a plane wave, as you see, propagating in that direction. And you have some areas where the medium is compressed and some others where it is decompressed because of an acoustic disturbance. So light will travel slightly slower or slightly faster depending on the local density of the medium, right? In other words, light, the propagation of light will be affected by the presence of a sound field. Now, this effect has found many applications in optics. It's been largely used for, say, using ultrasound to modify properties of light, but it has been much less used in acoustics and specifically in the audible frequency range because of both technological as well as methodological limitations. I mean, I will discuss some of these. But the key idea is that these acoustic pressure fluctuations that will influence propagation of light will therefore act as phase shifts in the phase of light, and these phase shifts can be measured with an interferometer, right? So here we have these phase shifts. As you notice, they are proportional to a line integral of the sound pressure field. So basically, we have here the sketch of an interferometer where we have a light beam that it's sent out. Notice that it's being sent out across a sound field, and it is impinging on a rigid object. So we are not measuring a vibration, and then backscattered into the laser or into the optical system, and then we have a reference beam by which we can determine the phase shift. So basically, just comparing what's the phase shift experienced by the beam that traversed the sound field compared to the one that didn't, right? So in this way, this is basically the line integral of the sound pressure field that we have here. So you can probably anticipate this gives us just the one projection value of the sound field, but that's not enough to reconstruct it. So naturally, we would need multiple projections. That's typically one would perform these sequential measurements to obtain a tomographic image of the sound field. So basically, that's the general idea. But there's an issue that conventional tomographic imaging methods are not suitable for the problem that we're dealing with, essentially because of the number of measurements. So conventional tomography requires far more measurements that we can acquire like this, and also typically they require some restrictive configurations where, say, you must have beams in parallel rotated at certain angles and so on. Of course, depending on the method. I will not enter on details on that. We can elaborate if relevant later. But basically, these two issues make it impossible for conventional tomographic methods work for the present problem. So what we've been doing in recent years was actually to develop a tailored method for acousto-optic sensing, where, I mean, the essential idea is that unlike conventional CT scanning and so on, where basically you are scanning something because you want to know what the object is, right? So you want to find either an anomaly or basically have an idea of what is the object that you're scanning. In our case, we do know that we are scanning a wave field, right? So therefore, it really improves a lot of reconstruction if we incorporate that by using elementary waves, in this case, plane waves, to as a basis for interpolating the data. So in that case, what we have is some projections, some coefficients, and then we are actually requiring that what we are scanning is a solution to the wave equation. This in turn results in us needing less measurements for performing the reconstruction, and importantly, it also enables to have arbitrary projections of the sound field, so we don't need, say, certain parallel lines or certain coverage. It can actually it can be arbitrary projections, and this makes it possible to use the technique in situ with fairly few measurements. Yeah.
Should we ask questions at the end? Or can we ask now?
As you prefer.
So a couple of questions. When you say
Yeah.
sound field, is this instantaneous or is this expanding field that you're referring to?
Yeah, good question. So here we're looking at the stationary sound field. Yeah, that's largely because we are considering sequential measurements, as I said, and therefore we're looking at the, in principle, harmonic sound fields. Yeah.
So, for example, when you're measuring the stationary sound, is there usually a sound source? Like, is this experimental or is this more theoretical?
Yeah, it is experimental. I will move on to some experiments, and it will.
And when you say where you're doing the different elementary waves, what is this? Is this the sound that is different elementary waves, or is it the light that you're modulating? Yeah,
so it's the sound. So it's the sound field that we're expanding into an elementary wave basis. So then it could be plane waves and its solutions to the wave equation, where we say the data that we are measuring is then projected onto an acoustic wave basis.
So you emit different types of waves, or when you receive them, you decompose them?
It's when we receive them, we decompose them, right? So then there is, we'll show that in a moment, but say there is a stationary source in the sound field, then we can scan it, and then the data that we are obtaining would be this, would be stacked in a vector S, and then you would have a transfer matrix and coefficients, and in this transfer matrix is the acoustic waves, so plane waves or spherical waves. And then, yeah, then you actually have an inverse problem where by estimating the coefficients of that basis, then you can reconstruct the sound pressure instead of the projections, right? So I'm sorry I kept it fairly general, so I didn't enter into those details, but I hope it makes sense. In this case here, I will use the question to elaborate if that's okay. But in this case here, what we have is the projections, then some coefficients, and then a transfer matrix. So what we would do is obtain the coefficients and then use these same coefficients to go to space domain and not projected space domain, right? So then we would recover here some pressure that's a function of R instead of the line integrals.
And it's also a function of time, like you're measuring the actual kind of oscillations across time.
Yeah, so we are implicitly, because we are looking at the harmonic sound fields and control, so we are measuring, essentially we're measuring frequency responses and then converting to time domain. If we have multiple laser heads, or there's also some systems that enable to have multiple measurements simultaneously, then you could potentially do instantaneous acquisition in time domain. But because of having a single sensor, then we are using we're assuming stationary field. Yeah.
But you sample the acoustic properties of the space this way, so you can get a really nice impulse response.
Yeah.
Sweet.
Yeah, exactly. So, yeah, correct. Great. So yeah, so I will then. I think some of the things hopefully become also a bit clearer on looking at the experiment. So here we have a first test that we perform in the anechoic chamber. So we have this laser Doppler vibrometer. It's a scanning laser Doppler, so it has a set of mirrors that were basically the laser beam can be steered automatically, and we are pointing it at a rigid steel bar here. Yeah, so here you see basically the shape of the measurements. We are scanning about 100 lines in a fan shape, and then we have a loudspeaker outside here that we are controlling, so we are actively driving it, and this is generating a sound field. And as I said, we're measuring sequentially these 100 of projections, and we are also monitoring the vibration of the bar to make sure that it's indeed fixed, and what we're measuring is the acousto-optic effect and not the vibration of the structure. So the results that we obtained look like that. So basically, you can see that within the measurement aperture, we are recovering the sound pressure, and you can see the real sound pressure of a wave that's more or less diverging from the position of the loudspeaker. And then you can also see that outside measurement aperture, that you can actually extrapolate and to some extent predict what the sound field would look like. And this is indeed because of using this interpolating wave basis that we were just discussing, right?
So
yeah,
I have another question. When you generate, when you're doing these measurements, are you doing them, is it because you're scanning so fast that the wave is relatively static, or do you repeat them and re-emit every time? And
we repeat them. So what we're doing in this case is emitting some stationary noise that it's broadband and then measuring at one point. So then we have a frequency response for that beam and another and another and another. And then from that, we just have, like
you're not changing the sound. You assume it stays. At least while you're scanning, you assume it stays.
Yeah.
Leave the speaker on, the transits die out.
Yeah.
Then you can shift the frequency or shift the sound.
Exactly. Then you have both space and frequency, or you transform space time.
so you transmit the wideband noise, and for each of these sort of line measurements, you're able to measure accumulate the sort of the integral of the
field.
of the field, and you get a single point.
Yeah, you get one single value. Yeah.
And then you're scanning geometrically. And then from all of these values, you get like 1 point from each of those. So it's a projection.
Yeah. Exactly.
And so the lines are basically the projections, and then you do the inverse problem in order for you to
reconstruct the field. Yeah.
Is there any assumption on the source of the sound, or just that it is wideband? Like, is there any prior on the sound?
No, there is not. So I mean, the only implicit prior we've used when using this wave expansion is that the object should satisfy the wave equation, right? So we're using an interpolating function that's a solution to the wave equation, right? So in a way we are, so say if instead of scanning a sound field, we would scan, I don't know, a different object, it would tend to look a bit wavy, if you see what I mean. So sorry to put it a bit trivial, but it's, yeah.
And is it always a line, or does it, like the structure that you're using, does it matter if it's curved or?
It can be curved as long as you know how long is the path, but that's something that can be measured automatically, right? So it can be, I mean, I know I don't have it on this. I have a backup slide that shows, say, different projections combined at different distances and so on.
And last question, why do you have enough degrees of freedom using these measurements to be able to do this? Like, how is that related to the resolution that you're doing reconstruction?
Yeah, that's a very good point, actually. So the way that we assess that is by looking at the null space of the transform matrix, and basically seeing what directions of propagation might be ambiguous, right? So if you notice, for example, in this scanning that we have here, the wave is traveling from here and in that direction, right? And then it's traversing the beams more or less perpendicular, right? But if you could imagine that if the source was, say, here and traveling towards the laser head, you cannot resolve that direction as well, right? Yeah. So, for example, in some other cases, I think later I'll show that backup slide, that you can choose multiple positions for the laser head and then scan in different directions, so that then you don't have any ambiguities about the direction of propagation of wave.
Could you start to use the radar transform and do real tomography?
Yeah, so actually that was the starting point that we did, but then the thing of the radar transform is that then you actually require to have, because you're doing the Fourier transform, you require parallel lines, and that gives you like one line in wave number k space, and then you need to rotate it, right? Actually, there's one experiment later that I showed you, we did that. So in principle, you can use it, but then that in say in situ measurement, it would be very hard to rely on having a setup that has this geometrically regular scan, right? Whereas on the other hand, if you would use what's called the SART methods, which is an algebraic projection, basically instead of what you have as values, each pixel has a given value, and you try to reconstruct that. then you can use arbitrary projections, but then you require a lot of data. And that's actually what I'm showing here. So using these 100 projections, you would use this state-of-the-art city reconstruction approach. Then you see that there's not really enough information to reconstruct pixel by pixel what the field is like. Right? So of course, if you have a proper CT scan, you would have millions of projections in all directions, and you could basically reconstruct the object pixel by pixel, right? But we cannot do that. Yeah. So yeah, thanks for the very good questions. Any? Yeah. Should I continue? So this is single wave on an anechoic chamber. Now things get a bit more real, and we look at measurements inside a conventional room. It's an unfurnished room in our labs. And basically what we have is here the scanning laser head. We have a microphone here that we use for reference, just a conventional high quality measurement microphone, just to have a quantitative reference of the measurement. And we have a source here on the side. So this is, once again, we measured frequency responses and then transformed to time domain. So what we are looking at here is different snapshots in time domain of the sound field inside this volume. So notice that we are measuring on this sort of pyramidal shape, and we're reconstructing on a kind of shoebox shape that's larger than that, right? And what we can appreciate here is the direct sound from the loudspeaker arriving from here. There is a reflection of the sidewall that's trailing just behind. You can see a reflection from the floor here, and here the interfering waves. So it might be easier on this if we look at the movie. So here we have the actual reconstruction. Here it's a numerical simulation to verify that the reflections and the waves that we're seeing are as should be there, right? And then what we see, I will play it again. Basically, we see again the direct sound. Let me just see if I can play it again. Yeah, so we have the direct sound from here trailing that reflection from the wall. We will see now the reflection from the floor. This direct sound is being reflected by the opposing wall. You see the interference, kind of checkerboard pattern there. Secondary reflection here from the wall on the floor, and then later reverberation where you have multiple overlapping reflections of less energy, right? So yeah, so essentially what we have now is this reconstruction over volume that we have obtained without actually immersing a transducer into the reconstruction domain, but we have acquired this remotely and non-invasively. I guess the non-invasive concept, it's a bit the quotation marks here because we have a huge laser in the room, but at least we don't have a transducer in our reconstruction domain, right? So I guess if I say non-invasive, please, take it with that pinch of salt. But yeah, I guess an important point here is that we can also look at individual points. So here you have the reconstruction from the laser tomography at the point where we had the microphone standing there. So the microphone signal is here on the black. It's a black line, and the reconstructed one is the blue line. And you can see that actually the values of the sound pressure follow quite well quantitatively the measurement, the direct measurement with microphone. Also notice that the sound pressure levels are quite high. So this is a weak effect, so we'll have to drive the loudspeaker quite high. Later, as the energy decreases, then it becomes more noisy and so on. But it's I think a really good result to be able to have a quantitative and spatial reconstruction of a fairly large volume. If you think about it, you could also imagine this as if you have like potentially thousands of invisible or remote microphones that where you can pick from this volume. But then this is so far for the sound pressure. Another aspect that personally, yeah, there's a question.
Signal amplitude is a little bit lower, if your SNR is a little bit worse. Can you scan slower and overcome that?
Yeah. So you can do that. Indeed, so you can scan or try to reduce the noise. There is also some so the noise problem here. It's quite complex because you of course have the, let's say, the electrical noise that I guess it's what we think when we consider noise, but you also have that the laser head can vibrate because of the sample, and especially more than the head itself, the optics here, the mirrors are exposed, so they easily vibrate. So even the wall, if you are driving very loud, the source, it will, and especially towards lower frequencies, will vibrate somehow. So there is some of the noise that indeed can be solved by averaging, that it's say what would be the noise floor or self noise, and then there's other sources of error that are actually physical and you don't get rid of through averaging. Right? But yeah, it's a good point. Actually, I used the question to highlight that this is equipment that's designed to measure vibration, right? So we are actually using it for different purposes, and it's not tailored for measuring these weak signals, right? Some of the work that we're doing at the moment is to talk with our optics colleagues at DTU to see if we can have tailored setups that are actually better suited for this task. Yeah. Great. As I was saying, so far we've looked at pressure. One thing personally that I find very exciting is that because we know that our object, our waves, it not only helps us interpolate, but we can also look at other field quantities. So, for example, here we have a reconstruction. Here it's a side scan of the sound pressure, but we can look also at the particle velocity. So we can actually see how the acoustic medium is moving, or the fluid medium is moving because of the acoustic disturbance, right? So here we see, maybe you can notice that there's some sort of checkerboard pattern that's due to the sound being emitted by the source and mostly the ground reflection, but it's pretty strong. So then it generates this, say, these regions of, say, null velocity and some others of a stronger velocity there, and also the wall that's opposing it. So like a standing wave. And we can also look at the sound intensity, so basically how acoustic energy is flowing in that volume, right? So that's what we see here. This is the time average acoustic intensity. The source is here, and then we see how on average there's energy that's flowing away from the source, and then it has these circulatory patterns because of the different wave interference. And here we have a simulation, a movie of that. Let me just, let's see if I can get it play. Yeah, okay. So we see how this is this is instantaneous sound intensity. So we see how there's flows of energy towards the opposing wall, then some other being reflected, and this sort of circulatory motion of the intensity or the power vector. So that's actually something that's you really don't see with just the microphone measurement or this advanced microphones. Like, in a way, I think something that I find very powerful is that then you're actually capturing not just the given quantity in space, but also the quantities that derive from it, right? Just to give a bit of context, this could be useful both to understand, say, how a source radiates sound, but also, for example, how much of the energy in the enclosure is being absorbed by one or another wall, have some information about the boundary properties of the materials, and so on. So yeah, and then a final thing.
These measurements are valid.
Yeah, so in this case, we are, because of the good point, I'll go, well, because of the issues with vibration of the laser and so on, the results that I was shown, the final results were just at the band around 2 kilohertz, so they were monochromatic, and the previous in time domain, they are filtered between a couple of 1 point something kilohertz up to 5-7 kilohertz. This is also why when you look at the impulse response, it has this kind of burst because it's band limited, mostly because of the vibration of the optics, right? But in principle, I mean, it would be if the optics were shielded away from the actual sound field, then you could have a much broader reconstruction. And then a final thing I wanted to mention on this is, so far we have looked at say reconstructing sound over volume, but another application where this is very powerful is actually to measure very close to complex vibrating sources to understand what is happening, not so much on the source itself, because for that you can just look at how a source is vibrating with a vibrometer, but more to understand how the fluid medium is behaving around the source, right? So this is what we have in this in these results. We have a vibrating plate, and we're scanning at a few centimeters from it, again pointing to this bar. And in this case, we have the measurement that we did is much closer to radon transformer. We have parallel lines, and then we're rotating this setup. But we're using the same reconstruction method. And I am just showing here, of course, we can get to the pressure, velocity, and so on. This is actually the sound intensity field above the plate. So the plate would be on this plane down here, and this is the volume above it vertically. And then what you can see is that there are some regions of space. I lost my cursor, there it is. So there's some regions of space that have a quite strong energy radiation, but only a small part of it is being radiated out to the far field, and that's the sound that we would hear, right? And what we can see is that the intensity vectors then are bending towards the source again. Basically, there's a lot of energy that's being emitted and reabsorbed by the source. So there's a lot of energy that's confined into the near field.
Effervescent wave and the left wave, those
Exactly,
waves
yeah.
evaporate.
Exactly. So this is the evanescent waves that are interfering with some of the propagating ones. They generate this circulatory motion. And again, this is something that it's hard to see otherwise, right? And the potential of this, it's especially at high frequencies, where you would need a very dense, because you could also measure this, and you can do it with an array of microphones, right? But if you're interested in high frequencies, then you need a very dense array that's close to the source, and it's very invasive. It really modifies the sound field, right? But in this way, you are not disturbing the sound field radiated by the source. So yeah, so that's what I wanted to mention about this acousto-optic effect and novel sensing methods that are inherently spatial. I hope that made sense. And the other topic I wanted to touch upon is what would be sound field reconstruction. And that's valid both if you are looking at new sensing methods or conventional sensing methods with microphone array. In this case, I mean, the concept is, as I mentioned before, no matter what, you're going to have a finite set of measurements confined in space. So depending on how you process the data, you might be able to interpolate and extrapolate to have basically a reconstruction of the sound field. So traditionally, this is done expanding the sound field into elementary waves. As we discussed, it could be plane waves, spherical waves. In some applications, the use of spherical harmonics is very, very widespread. And in recent years, some of the advances that we're seeing in this field is actually to try to incorporate as much physical structure as possible in the reconstruction method. So basically, your prediction can be better, right? So some of the work that we've done in the group has been, so this is actually a similar problem to the previous. Instead of using a laser scanner, we just have a conventional microphone array, and then we can use wave expansions to basically predict what's happening on the face of a complex source, in this case a guitar, but it could be any other acoustic source. Right? Now, specifically, a problem that is very relevant is sound fields in enclosed spaces, rooms, and so on. We spend, I think it's about 80% or 90% of our time indoors, and a lot of acoustic communication happens indoors. So this is a very relevant scenario to address, and a difficult one. But luckily, rooms and sound fields in room have some properties that are very general, irrespective of, say, the size of the room and the specific geometry and so on. Where, for example, in this case, if you have a convex room, you know that there's going to be a first arrival with most energy corresponding to direct sound, followed by early reflections from floors, sidewalls, etc., a few higher order reflections, and then some late reverberation. And this, in most cases, is going to decay exponentially with time, right? So, as I was mentioning, most reconstruction approaches would be you have a set of measurements. Imagine, say, spherical arrays, very commonly used in rooms, and then you would expand this into spherical harmonics, and then you can then use this either for reproduction, say binaural, or an array of loudspeakers, something like that. But by expanding the field in spherical harmonics, you are not incorporating any information about the room, and you're not incorporating any of these generalizable properties. Right? So a specific method that we've been looking into is, I won't enter into very many details, but essentially it's trying to incorporate this structure into a wave basis that accounts for a direct field, early reflections, and late reverberation, with some constraints on the energy and how this evolves about time and so on. And we are formulating this in a probabilistic model, formulated as a Gaussian process, and solved using stochastic variational inference. So basically, this is a time domain model, which turns out to be huge because you have many samples in time. And therefore, we used stochastic variational inference, where basically we're parameterizing a distribution and then trying to solve the inference problem through this approximate distribution. Right? If there's any questions about that, I'm happy to take them, but I don't want to enter into so many details now. Essentially, let us look at some of the results. This is a classroom in DTU where we perform some measurements. You can see this is a robotic scanning arm. So these are also sequential measurements. This could have been done, say, at once simultaneously with a spherical microphone array, but we wanted to have a bit more control and over the data that we were acquiring. Basically, what we are measuring here is a spherical grid of points in the more or less the center of the room here. So we have 48 microphone positions. And it's this data that we use to try to reconstruct and to extrapolate the sound field. And then we have a line of reference points here that would be the true field that basically spans the width of the room. And then we're using that line basically to see how good our predictions are. Yeah. So
how do you measure that? Like how closely your measurements match your kind of round trip measures your predictions? Is it like straight NSE or like you got some?
So I mean, we'll look at it. So basically, then we take the data from the spherical array and then we construct the field along that same line compared to the measurement, and then we can look at it both qualitatively by simply looking at the waves that are arriving and what are the properties, as well as also quantitatively by looking at error metrics both in frequency and in time domain. But
like you have an early reflection, which is like a little bit late, right?
Yeah.
Again, the large error, but
Yeah, Yeah, exactly. So that's a very good point, and that's why I didn't want to jump from here to error metrics, but the next slide was actually just seeing how the reflection pattern would look like to have a bit more of that, say, qualitative assessment, right? So this is the data. So the true data, notice this is space. So this is the line across the room, and this is time here. So we're basically looking at when its wave arrives at which position of the line array. And what you are seeing here is first the direct sound. You notice it's the most curved wavefront, and of course that arrives earlier with most energy. Then you have the reflection from the floor. Here, this is the reflection from the ceiling. That if you notice, it's slightly lower in. It has less energy because the ceiling has some absorptive material, as most classrooms do. And then we have here the arrivals, so lateral arrivals, and also reflections from the back wall. Important to notice is that the dashed lines here, it's basically the size of the spherical array that we are measuring with, right? So basically the data within these dashed lines is that we're measuring with the spherical array, and then we're trying to predict both what happens inside the sphere and what happens outside. And this is the true reference data. If we would use what's state-of-the-art or maybe more standard methods for this problem, like here we have the lasso, or essentially compressive sensing using just the plane waves. This is commonly used in audio reproduction. And basically, you notice that the data inside the array is correctly recovered. So you have the direct field, the ground reflection, ceiling, back wall, lateral reflections, and so on. But then the data that's extrapolated is basically completely off, right? Because, as I said, we are not incorporating that structure of the sound field in the room. And this is, well, I'll get to that a bit later. We can use another reconstruction method, in this case using a Bessel kernel as a Gaussian process. Essentially, this is a model that's used for reconstructing reverberant sound fields, and we see that pretty much the same thing inside the array area. This is correctly reconstructed, but then outside it's basically predicting a sort of reverberant field. So this late part is more or less correctly recovered, but not the early part. So when we look at the method that incorporates this spatio-temporal structure, we see that the reconstruction is much better. So inside the arrays, like the other methods, but it's especially outside that you see the direct field is very well recovered, the ground reflection and ceiling reflection. Then you notice that the side walls, they tend to underestimate the energy towards the far end. And it's interesting also to see this reflection here, because the curvature here, it's less, or it's less drastic than the model cannot recover it correctly. So it basically traces two superimposed wavefronts, right? But all in all, the prediction is much better. So to wrap up, the significance of this is that, so we are measuring over a sphere that's about this size, and we're able to, with a fair accuracy, reconstruct over 5-meter aperture. In this case, we're doing a line because it was convenient to measure, but the reconstruction is expected to be equally as good in a spherical volume of 5 meters than a meter, right? So when you look at these sketches here, that's almost the entire room, right? Or a good 2/3 of it. And in how this relates to, say, conventional audio techniques is, for example, if you would measure with a spherical array and code into ambisonics, what you're getting is something similar to this, where inside the array you see, okay, there's a wave arriving from the front. Here there would be one from the floor, side reflections and so on, but you're very much confined to the data that you have measured, right? Whereas in looking into approaches that are a bit more general and ambitious in terms of space, then this actually enables to navigate the sound field, meaning that you can reconstruct the sound field at the point that you measure, but you could potentially also get a spatial impression of what is the sound field elsewhere. So potentially you can be immersed in it and move about it with a fair reconstruction. Yeah.
So this is giving you the, like, so if you know your source signal and you know the sound field at all the different points, you basically have a transfer function like from the source to everywhere kind of inside this spatial domain, right?
Yeah.
So do these same kind of like modeling decomposition, does that also help you, like, let's say you wanted to move your source to a bunch of different locations and kind of like scan the rooms and you get kind of all the different pairwise.
Yeah.
Does this also help you interpolate between different source locations? So like you wouldn't necessarily need to, like do a super dense grid.
Yeah, this is a good point. I guess that it is a very good question actually. Then how would you do like more multiple source to receiver location? I think it can, in this case, the way that I would see that it's more through a combined measurement, a combined model, either using some mode shapes in the room or image sources or cluster of points to both model the source and receiver. Then after all, this is also a reciprocal problem, right? So potentially you can do that. I don't think it would work exactly how it is implemented here. So this is very much constructed for a single source measurement. But I would certainly see that as an option. Yeah. It is a good point. So we have addressed that specific question, that looking at only low frequency sound, because let's say we're a bit more, or the specific source to receiver or source listener response when you have strong modes in medium enclosures can be quite strong. So we have looked at that problem. We have not looked at it in a broadband sense in time domain. But yeah, it's a very good point. Yeah. Okay, great. So just as I said, some quantitative measures. I won't elaborate much here, but we see both interpolated and extrapolated data, especially the early part of the response is quite well predicted by the approach that we presented. Then it's interesting how the later part of the response, then the assumption of this reverberant kind of conventional model works well, which then comes as a sort of relief, because we could use the more computational heavy model to reconstruct the early part of the response, which is also very important perceptually, and then later in the reverberation switch to a much lighter and ineffective model, right? And another point to make here, when we look, this is frequency response and the spatial coherence, so basically the similarity in space is a function of frequency. And this is, so when you look at it in the interpolated regional methods, do more or less okay with their differences, but it's especially in the extrapolated region that you see the model we were looking into is much better. And the significance of this is that the coloration that we would perceive is very much a function of frequency. So just by recovering the early or the direct field and some of the early reflections, then you would get a much better or realistic impression of what the coloration, what the timbre of a given sound would be like. Yeah, so that would be just reconstructing the field over a longer time span. As we see, as I mentioned, the direct field is particularly, or the early response is recovered quite well. And that's what I had just to wrap it up. I hope I have illustrated how we're trying to advance our ability to sense and process acoustic and audible sound beyond what would be time frequency processing, and also beyond what would be considered the standard spatial audio techniques. So looking a bit ahead towards including more aspects of space and so on. And yeah, personally, I think the outlook is exciting because we're seeing quite significant advances both in sensors and signal processing, machine learning techniques, as well as computational methods. And yeah, that's the daycare alarm to pick up my son.
Thank you.
Yeah, thank you very much.
Any type of questions, you have to run to daycare.
No, I have time for questions. That's
I
okay.
have been in that position. I think we have a lot of interest in acoustics and the kind of problems you're talking about. Anything from the floor? Maybe I can ask one simple question. We can talk a bit about this, but I thought about systems like your laser system for looking at airflow in large spaces, because it's the kind of the DC very low frequency, but actually you don't have to worry about the walls vibrating. It's just changes in air density because of airflow.
Yeah.
You need sensitivity for getting small airflows, but if you map out the airflow dynamic, it's a lot of value in HVAC and stuff.
Yeah.
And I was thinking when we were talking about that at one point, to try to, from one point scan the entire room somehow. I was thinking about putting spherical mirrors, for instance, in a corner. You scan the room normally, you hit the mirror, suddenly you have a reflection that can, within a small angle, scan the room from another direction. Of course, you have to get the data back along the laser.
Yeah.
But would that be useful for this? So from one point, you can get multiple angles instead of having multiple lasers. We're still integrating along the same beam.
Yeah, I think that's a good point. Also, I mean, eventually the data you have a single emission delay. So if you have a specular reflection from this sort of mirror sphere, that won't be scattered back into the optical system, but eventually the wall or the object would bounce off. It would, so then you would have like a multi-trajectory point, and then that's a very interesting point.
Anybody online?
What specifically? So I noticed like a lot of your experiments are like 4 kilohertz or 5 kilohertz and below. What are the specific challenges with like much higher frequencies, like tens and hundreds of kilohertz?
Yeah, that wouldn't be so challenging. And the effect is the acousto-optic effect. Are you referring to the acousto-optic effect or?
Well, I guess both the acousto-optic effect and the practical limitations of like the interferometer mirrors.
Yeah. So actually, the acousto-optic effect it's quite strong at higher frequencies. So there's a proportionality to the angular frequency when you look at it, and therefore this is one of the reasons that historically it was first used in the ultrasound brains to both in optics and also in ultrasonic acoustics. So that's not so much an issue. It's just one would need a different instrumentation, different setup, because you're having much smaller wavelengths, right? And what's then more challenging is on the lower frequency end, because both the effect is slightly less sensitive, and also you have a higher background noise, walls tend to vibrate more, and objects and so on. So it is more challenging on the low frequency.
That's where the airflow would live, but it's almost a DC. So that's where it is.
Yeah. But I think so. After all, like what we're measuring indeed is density changes in the medium, right? So if the density change is strong enough, then you should be able to see it, as is done or has been done traditionally with Schlier and imaging and so on.
Any more questions or any questions from anybody online? You might be able to speak up. Do you have your audio on?
Yeah.
Efren does have to get to daycare at some point.
Right.
He'll be also around.
Yeah. So this is the first alarm. Then there's a second one when I really have to run. Right? And I have a good 40 minutes. So this is knowing that I maybe tend to get caught on my work. So.
Is that possible to realize something like that? Phase area.
Actually, they have it, and you could use a diffractive beam steering. You can have multiple beams, some beams move it in much faster than the mirror potentially. You just have the capacity to put LCD done. So you could could use a diffractive beam steer.
Yeah.
They exist. Yeah, with that, you can make multiple beams, one beam, steer beam. It is like a booster.
Yeah.
Assume that might be faster than.
It'll be faster.
Yeah. Also, there's so even for vibrometry, there's I think the last few years they have put some systems where you have I think 34 simultaneous beams measuring, so you have like multiple laser heads that perform that. So
The old Connect pretty much was that too. It was just a static program to take one beam, split into multiple. But you can make that also dynamically, much of the phase spectrum. I've seen devices that do that.
Yeah. I was wondering to which extent also you have like a particle image velocimeter or something that you then decompose the light into a sheet of light, and then it would have multiple photodetectors and so on. But then it's it's an issue when you would need to at least in interferometry what to do with the reference beam, how to do modulation and so on. But I think I mean I hope at least that things go that way. So,
It's great to see this get closer to something that's practical and usable. I'll show those pictures of the acoustics inside a room without putting a microphone everywhere, which would naturally disturb the room or move the microphone. It's tedious. So it's great to see. Good. I think you struck a lot of ideas. Fidel's team do a lot of underwater acoustics. You probably know about that work.
Yeah.
That part of the team is here at Fidel. So there'll be more connections, I'm sure.
I'd love to do like to talk a bit.
And if anybody's interested in reaching out, let's resident here for the people online. Definitely is around.
Yeah, please do. I'm here until October. And
Great.
it will be a pleasure.
Okay. Well, thanks again, Efren.
Okay.
And you can make it on time. They don't like it when you